All right, good morning. This is for Physics CP, and the unit is dealing with waves. I have a little section here I'd like all of you students to record and keep it in your notes. When we talk about a section of the electromagnetic spectrum, it varies continuously. It's like a rainbow. So when you look at a rainbow, where's the cutoff between when you say, oh, that color is red and that color is orange? Well, over the years, I'm sure someone has figured out and defined that, right here is where the change occurs. Well, the entire electromagnetic spectrum, not just the rainbow, is continuously changing. So what I've done is I've jotted down what I'm going to use as the limits for the range of different values across the electromagnetic spectrum. So EM spectrum, electromagnetic spectrum, have two columns. First is the name of the region, and the second is what range does it entail. So starting off, the first region on the electromagnetic spectrum, the longest wavelength, the lowest energy would be called the radio wave region. And we're going to say that starts when you have a wavelength of 1 meter and it goes up from there. And so I wrote kilometers with a plus sign, but radio waves can go to hundreds of kilometers in wavelength, and we would still call those radio waves. The next category ends at 1 meter. Okay, so anything longer than a meter would be called a radio wave. Anything shorter than a meter, down to MMs, well, I remind you from the physics and chemistry reference sheet, June 5th, 2019, page 1, or revision 8, that a millimeter is 10 to the negative third power meters. And it is the spacing of two tiny lines on a typical meter stick. So microwaves are down to a millimeter in length. So anything that's greater than a millimeter, which you can kind of show as a gap between your fingers, and 1 meter, that would be the microwave range of the electromagnetic spectrum. Then, so we're moving our way to shorter and shorter wavelengths, higher and higher energies, higher and higher frequency, because all of these travel at the speed of light in a vacuum. So the next category up, I would call it the infrared range, and it says 0.7, that's an 8 that I just stuffed in there yesterday, and there is a Greek prefix. This one is the micrometer prefix. Microns, as they are called when you talk about length, are millionths of a meter, 10 to the minus 6. So if I took a millimeter, 10 to the minus 3, and I scaled that to be the size of a meter stick, then on that scale, the micrometer would be a millimeter. Or in other words, a micrometer is 1,000th the length of a millimeter. Pretty tiny. Anything longer than 0.78 microns up to 1 millimeter, that would be the infrared band on the electromagnetic spectrum. Anything shorter than that takes us to the next category. So visible light. Now the units here are nms. I remind you from the handy dandy reference sheet that an nm is a nanometer. A nano is 10 to the negative ninth power. A micron is 10 to the negative sixth power. So there are 1,000 nanometers in a micrometer. So on this reference sheet, when it says 780 nanometers, that is 0.78 microns. So these are the same number here, just written in two different Greek prefixes. 0.78 microns is 780 nanometers. The range of visible light is as short as about 380 nanometers and no longer than about 780 nanometers. In this range is the entire rainbow of light that you can see, with red being the longest wavelength and violet being the shortest wavelength. But what's shorter than violet? Ultraviolet. And so, if the wavelength becomes even shorter than 380 nanometers, which are billionths of a meter, down to, let's call it 10 nanometers, that would be the ultraviolet band. And now the energies are getting high enough to do real damage to living tissue, right? You can get sunburn from ultraviolet rays and other bad effects. What about shorter than ultraviolet? Well, that next region would be called the X-ray region. And you're somewhat familiar that X-rays are used to look right through human beings, and we can use some nice processing equipment now and examine the inside of your body. So from 10 nanometers down to 0.01 nanometers. And this is on the size of an atom. I think an atom is on the order of a nanometer in diameter, some of them. We could look that one up, but I'm not going to. So X-rays can be on the order of the spacing of electrons in atoms in a crystal structure, I think. And then finally, anything shorter than that, we're going to call it a gamma ray. And notice these are the same values here, but in different units. A picometer, I remind you, is 10 to the negative 12th power. A nanometer is 10 to the negative 9th power. This is a factor of 1,000. This is a factor of 1,000. From micro to milli is a factor of 1,000. From milli to base units is a factor of 1,000. From base units to kilo is a factor of 1,000. Kilo to mega is a factor of 1,000. Mega to giga is a factor of 1,000. Once you get above giga or below pico, all the Greek prefixes are a factor of 1,000, 10 to the third power change. So as you look at this, 10 picometers, move the decimal point 3 places to the left, 1, 2, 3, sure enough, that's 0.010 nanometers. All right, write this down because I want to be able to ask you basic questions like, oh, I have this photon and it has a wavelength of 38 centimeters. What kind of wave is it? All right, so if I gave you a photon whose wavelength was 38 centimeters, you should have said, oh, according to my notes, that's between a millimeter and a meter, and I would classify that as a microwave. Excellent. Well, no need to have this reference sheet here anymore. I can just ask you because you wrote it down and took notes. So, what would be the category for a wave that is 6.2 meters in wavelength? 6.2 meters in wavelength. All right, so if I have a wavelength of 6.2 meters, that puts it firmly in the range of radio waves. Radio waves. What if I told you, oh, I am studying different photons, and here's one whose wavelength is 555 nanometers. 555 nanometers. What kind of wave is that one? So a wavelength of 555 nanometers is indeed visible light. And I could even try to challenge you about, so what color do you think that might be? If 780 nanometers is red light and 380 nanometers is violet light, 550 nanometers is basically yellow light. All right, yellow light. Let's see. Suppose I told you I have a wavelength of oh man, 0.52 microns. 0.52 microns. What kind of wave would that be? 0.52 microns is shorter than 0.78 microns. It's actually yellow light. Once again, it would be 520 nanometers. 0.52 microns is 520 nanometers. So one thing you really should be doing is getting very comfortable using these Greek prefixes and flipping between them and saying, oh yeah, I know the centimeter is about the width of my little fingernail. I know that a kilometer is something where it takes me like 15 minutes to walk it. A micron is a thousandth of a millimeter. Okay, so you have some work to do on memorizing your Greek prefixes. All right, coming back from our 3-minute break, it's time to start teaching you some of the details on this physics and chemistry reference sheet dealing with, for example, sound waves, the speed of sound in air. It states, this is a formula, and the formula says the speed of sound in air is 331 meters per second. But wait, there's more. Add to that 0.6 meters per second times the temperature in degrees Celsius. So if the temperature is 0 degrees Celsius, then the speed of sound in air is 331 meters per second. If it's 1 degree above 0 on the Celsius scale, so that means, about 33 degrees Fahrenheit or so, between 33 and 34, yes, I know. Then you add 0.6 meters per second to this, and you'd say, oh, the temperature is 331.6 meters per second. And really, generally, you're going to be rounding that up and saying, well, that's 332 meters per second to 36. So that's how that works. And we should practice it a little bit, I'm sure, because there's a couple of temperatures that we tend to use all the time. So random volunteer is about to tell us if the temperature were 20 degrees Celsius, what would be the speed of sound in air? If the temperature were 20 degrees Celsius, what would be the speed of sound in air? All right, so my students report to me the speed of sound in air at a temperature of 20 degrees Celsius would be 343 meters per second, and I agree. Now, let's do a few sound problems that maybe you should be thinking about as we do this. Do some little critical thinking here. Just suppose you see a lightning bolt somewhere striking the ground, and you're way over there someplace, not to scale. As soon as you see the lightning bolt, you start counting to yourself. 1, 1,000, 2, 1,000, 3, 1,000. If you happen to have a stopwatch handy, then yeah, you could use your stopwatch function and start, timing. And what you want to time is how many seconds go by between the moment that you see the flash of lightning with your eye and you hear, imagine that's one of your ears, hear the sound of the thunder with your ears. All right, so a student says 4 seconds of time go by between when you see the lightning flash and when you hear the thunder. Now, I got to give Galileo his due. The speed of light is not infinitely fast. So some time does go by between when the lightning flash occurs over here and when you first see it over there. But the speed of light is a million times faster than the speed of sound in air. And for all practical purposes, we're going to treat the time delay as being 0 seconds. So we're going to claim that the moment that you see the light is the moment that it actually occurs here. The reality, of course, is when you get to astronomical distances, we can't make that claim anymore. Okay, but for here, with between the horizon and ourselves, the speed of light is essentially instantaneous as far as human response capabilities go. And so now my next question is, oh, what happens to be the temperature of the air on this occasion? So my students tell me it happens to be a very hot day. The temperature, and I'm using capital T for it, don't confuse that with period from our other units, is 36 degrees Celsius, which makes it a sweltering hot summer afternoon, I suppose. Calculate, please, what is the distance from the lightning to you? And express your answer in units of meters. What is the distance in meters from the lightning bolt to you on a day when the temperature is 36 degrees Celsius and it takes 4 seconds for the sound to travel through the air to get to you? Okay, my students and I agree it's 1,410 meters, which would be 1.4 kilometers if you want to practice that skill. And would that be more than a mile or less than a mile? Well, the handy dandy physics and chemistry reference sheet, June 5th, 2019, page 1, mentions that 1 mile is equivalent to 1.609 kilometers. So if we're at 1.4 kilometers, then 4 seconds puts us at a little bit less than 1 mile distant. You should still strongly consider seeking shelter. Don't go standing under a tall tree to stay out of the rain because people have died from lightning strikes under that circumstance. Uh, in my lifetime, there's been several notable instances where multiple people died. A Boy Scout jamboree comes to mind. All right, so hmm, next question. By the way, that one you solve by first calculating the speed of sound in air, then multiplying that by the amount of time that it spends traveling at that speed. Now, suppose there happen to be some railroad tracks going towards where the lightning hit the ground. And railroad tracks, you may or may not know, are basically iron rails. The speed of sound in iron is listed on this table. Speed of sound in various substances, air, 0 degrees. Maybe for helium, the temperature matters, but for these other substances, the temperature doesn't matter. They don't vary significantly, and we're not going to be asking you, oh, what if the water is at 30 degrees? It's not going to matter. But iron is listed here, and railroads are made out of iron. And it says the speed of sound in iron is 5,130 meters per second. So based on that, how much time would it take for the sound to travel along the rail the same distance? Calculate, please, how much time in seconds would it take for the sound to travel through the iron rails? Okay, so to solve this new question, the question was how much time does it take for the sound to travel this distance? The distance is now fixed at 1,410 meters. And what's changing is we're going to use the speed of sound in iron, which according to the handy dandy table said 5,130 meters per second. So we take this, and the formula would be distance traveled is the product of constant velocity times time, and we're going to rearrange this equation to solve for time. Therefore, take 1,410 meters divided by 5,130 meters per second, and even in your head, you can see it's going to be much less than 1 second of time. The students I called on didn't quite agree with my result. I got 0.275 seconds. 0.27, and you're going to lose points if you don't round it correctly, by the way. So my calculator said 0.27493177739. Don't write that down, not even once. To 3 sig figs, the 0 doesn't count, it's just a placeholder. 2 is the first significant digit, 7 is the second one, 4 is the third one. So you look and ask yourself, what's the digit beyond 4? If it's below 5, you round down to 4. If it's 5 or greater, you round up. So 0.275 seconds is what you should write down as your answer in this situation. All right, let's do another problem. Oh, you are out on a nature walk and you see a cliff, and you are at the bottom of the cliff, some distance away from it. Oh man, what is the temperature? So the temperature is 23 degrees Celsius. And you shout out, I love physics at the top of your lungs. And it echoes off the cliff. And as soon as you shout out, I love physics, you start counting to yourself 1, 1,000, 2, 1,000, 3, 1,000. How many seconds go by before you hear your own echo? You count out that 5 seconds go by from when you first shout out, I love physics, and you hear the echo, I love physics. Okay, what is the distance from you to the cliff? Calculate, please. Okay, so just like yesterday, every student I asked gives me the wrong answer because you don't really have critical thinking skills about what it means to be an echo. An echo means the sound started over here and it traveled to the wall and then it bounced off the wall and back to you. So really, it covers the same distance twice in 5 seconds. So the true distance away is the time it takes sound to travel one way, and that's only half of 5 seconds. So the correct answer in this situation was 862 meters. First, you calculate the speed of sound in air at a temperature of 23 degrees Celsius, and then you multiply that by 2.5 seconds to get that result. I'm now going to turn our attention to, oh man, introducing you to Snell's law. That's this equation. And I can't even get that far without having to introduce you to the index of refraction. So if I cover this much before the end of the period, well, that's better than not covering anything more before the end of the period. So time to make up a story. And the story is one of you, dear students, goes off to the beach. Let's see. I have a student named Sean, and the student goes off to the beach. And so here's Sean standing on the beach where the waves hit the sand. So this is like a top-down view, even though I drew them horizontally. If I draw a top-down view, you just see a circle for the top of his head. I suppose I could have done that. So top-down view. Great. Well, as I look down from above, here is where the shore is. And then here comes the waves from the ocean, wave after wave after wave, heading to shore. Great. Well, it turns out there is a cute looking girl out in the water. And she's, oh, let's say over here. Okay. Not that you can make out what that is. So you can't see the rest of her. These are her ponytails or pigtails. These are her arms, allegedly. And we can't see the rest of her because there's a wave there. Great. Believe me, that's supposed to be a cute girl, not just a horribly butchered stick figure. And the question becomes uh, she wants him to rescue her. So she cleverly decides to pretend that she needs to be rescued. And so she starts going, help, help, trying to be very uh, convincing in the need for him to get to her in the least time. When we do this in a regular classroom with full interaction, where I call on students and they contribute to my drawings, which takes a lot more time, I ask them, so how should he get to her as fast as possible? He's here on the beach, she's out there in the water, here's the shoreline. What's the path he should take? And generally, the very first answer I get from students is he should go straight from where he is to where she is. That this is indeed the shortest path from him to her. And so if he goes straight towards her, how hmm, appealing it would be to her to see him always coming straight towards her. But then I point out to my students, well, he can actually run about 5 times faster than he can swim. So if he can run at, let's say, 2.5 meters per second, he can only swim at half a meter per second. So he's going to slow down a lot when he goes through all this water compared to when he was running across the sand. So then usually my students think about that and come up with a new revised plan that says, oh, we should minimize the amount of time that he spends swimming through the water. And so they usually suggest a route that looks like this, where he runs until he's directly across from her and then goes straight towards her. So run, run, swim. This minimizes the amount of time he spends swimming. That's true, but this is not the fastest route from him to her. And then students usually think about it some more, and then they come up with a new improved route. And they say, oh, what if he just goes a straight line directly to the point on the shore that is closest to her and then swims to her? Now he's running the shortest distance on the sand and swimming the shortest distance through the water. So that's the fastest route. And here is where I, earn my pay as a teacher. And I point out and I say, well, no, this isn't the fastest route either. There's a route that is a little bit faster. And the reason it is a little bit faster is because he doesn't run infinitely faster than he swims, which, by the way, means he would never get to her, right? Because that means he can't swim at all. But he runs 5 times faster than he swims. So if I kind of zoom in on this area and make an attempt to get you to believe me after it autofocuses, which it's not doing. Yeah, okay. So here's the point where she's directly closest to shore. If he aimed a little bit off over here, what would happen is he would be running this much shorter distance on the sand, but in return, he would be swimming this little bit more distance through the water to get to her. And under these conditions, a factor of 5-to-1 ratio between how fast he runs and how fast he swims. And I'm not doing this to scale, I'm just trying to get you to understand the concept. He would get to her in the least time. As long as the distance that he trims off running to the sand is at least 5 times the distance that he adds swimming through the water, it's to his advantage to aim a little bit more this way. If he could run as fast as he swims, then the first route would have been the fastest route. If he ran a million times faster than he swims, then this route would have been the fastest route. So if you can kind of imagine, these are the two boundaries. He runs at the same speed that he swims, or he runs a million times faster than he swims. Well, he runs 5 times faster than he swims. So in between these two extremes, there's the, somewhere around here is the fastest route from him to her. And you're starting to wonder, what the heck does this story have to do with any of this stuff on the reference sheet, such as Snell's law or the index of refraction? And so here's the story as to why I'm telling you this story and why it makes sense. Once upon a time, there was a king, and the king noticed that if you take a glass of water and you stick a pencil in the water, the pencil appears bent as you look to the side of the glass. And he pondered and he pondered and wondered, why does the pencil, which we know is straight, it doesn't actually bend when you go into water, why does it appear to bend as you look in the water? And so he offered a prize to anyone who could figure it out and explain it to him. Well, the guy who figured it out, his last name is Snell. So we call this thing Snell's law. And what Mr. Snell figured out is that light, like Chong, wants to travel from one place to another in the least time. In the vacuum of space, light goes lickety split, so to speak. It goes as fast as it's allowed to by the laws of the universe. When light goes through air, it actually slows down ever so slightly compared to being in a vacuum. When light goes through water, it slows down noticeably. The speed of light going through water is noticeably slower than the speed of light going through air or a vacuum. And light, wanting to travel from one point to another in the least time, changes its direction at this boundary between air and water. Just like our student changed direction going from running on the beach to swimming through the water. And sure enough, the amount of angle change has to do with the speed of light in one substance compared to the speed of light in the second substance. And so there is a value called the index of refraction. It's represented by lowercase letter n. And the formula for the index of refraction is on that reference sheet. It says it is the ratio of the speed of light in a vacuum divided by the speed of light in whatever substance we're referring to. So speed of light in a vacuum, that's what lowercase letter c represents, divided by speed of light in a substance, air, water, diamond. There's a list here. Index of refraction for various substances. And because the speed of light is in the numerator and it's always the fastest speed, all the indices of refraction can only go up from a value of 1. On this table, the highest value is the speed of light in silicon with an index of refraction greater than 4. And basically that means the speed of light in silicon is only about 1/4 the speed of light in a vacuum. I mean, we really slow it down a lot in this material. The reason diamonds sparkle has to do with the fact that light slows down a lot as it bounces around inside a diamond. Okay, well, here's water, 1.333. So that's the ratio of the speed of light in a vacuum to the speed of light in water, a ratio of about 4:3, right? So that means the speed of light in water is about 75% the speed of light in the vacuum. And that signals the end of today's educational experience.